get things started with a little bit of background. Today we're talking about tree-based models. And so last time we did decision trees from scratch. So we talked about basically like how decision trees work. We looked at this specific example where essentially we played with this idea of doing regression analysis on a data set of hockey players, and we're trying to predict the number of goals that a hockey player would score during the season. And I showed you that decision trees can be used for regression, and they have properties that are really handy. They're really easy to inspect. So that means if you look at a decision tree and you get a certain output, you can always explain why you got that output. You can follow the series of decisions that had to be made in order to sort that sample into whatever bucket it fell into and make the prediction that came out of the model ultimately. So that's one of the really big advantages of going with decision trees. It's one of the reasons that they're really my default go-to model, or at least tree-based models are. And this is really an advantage that propagates through all tree-based models. Any kind of tree-based model will have this sort of structure, and there are going to be clear reasons why every sample was predicted to have the value that it was, or the class that it was, depending on your problem setting. So that's why I wanted to expand a little bit beyond the conversation around decision trees. I want to make a couple of observations about decision trees first, just to motivate why it is that tree-based models are even interesting. Like, why don't we just stop at decision trees? Why aren't decision trees intrinsically enough already? The first reason is it has to do with an interesting property of decision trees that we talked about last time, and that's this idea of overfitting. So if you take a decision tree, which at the end of the day really is it's playing a game of 20 questions with your data set, except that instead of 20 questions, it's really however many questions you want to let the tree ask. The problem with that process is if you let a decision tree ask too many questions, if you let it ask as many questions as it wants of your data set, eventually it will ask so many questions. The depth of the tree will get so deep that you'll end up with basically one sample in each leaf node, one sample in each terminal bucket at the end of the decision tree. And really what that means is you've massively overfit, right? You have essentially a conspiracy formed around every single sample in your data set, so that you're by the time you get to this one sample, like you've asked, is this player between ages 39 and 40? Does their first name start with an A? Are they making between this amount and this amount? Like, you have so much detail that basically you're just memorizing each data point in your entire training set. And that's the definition of overfitting. That's something all decision trees will absolutely do, with one tiny little caveat that we can get into, but it's not terribly important the vast majority of the time. Decision trees will overfit 100%. You should be able to get 100% performance on your training set using a decision tree model, as long as you let it train as deep as it wants to go. That's a problem, of course, because overfitting isn't great. It's not something that we necessarily want to have happen. It's to some degree a failure of model generalization. And so we then get into games of, like, how do we prevent this overfitting from happening? How do we put constraints on this decision tree so that it can't play a game of unlimited questions, basically? By the way, the game of 20 questions itself, the whole reason that it's an interesting game is that you're limited to 20 questions. So whoever invented that game actually was thinking about this overfitting risk in the first place. If they weren't, if the game of 20 questions was a game of infinity questions, then basically, like, you could win it just by asking, like, so sorry for background, if you're not familiar with the game of 20 questions, usually you're trying to guess the name of, like, a famous person or a famous event or a fictional character that somebody else is thinking about. So you can ask them a series of questions, 20 questions with yes or no answers, and then you have to make a guess. Now, if you had an unlimited number of questions, you could just start by asking, for example, like, does their the first letter in their name start with an A? And it's like, no. Okay, does it start with a B? Okay, no. And then you keep going, and that would basically be a kind of gratuitous overfitting, right? This is the same phenomenon that we want to prevent these trees from doing, from creating like a very kind of tailored conspiracy around each data point that doesn't actually generalize well beyond the training set. So we want to find a way to prevent these trees from overfitting. One strategy is just that, to limit the number of questions the tree can ask. So you might say, okay, this tree is only allowed to ask 3 or 4 questions in a row. It can only have, in other words, a tree depth of 3 or 4. That's a parameter you can actually control in scikit-learn. It's called max_depth. That's the hyperparameter that you can kind of tune around to optimize your tree. But you could also do it in other ways that are somewhat equivalent, one of which is to say, okay, I'm going to limit the maximum number of buckets, the maximum number of terminal nodes in my decision tree. And in this case, we have, looks like 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 terminal nodes. Those are the nodes that a sample gets sorted in after it's gone all the way through the tree. And when it lands in a given node, then you essentially know what you're going to predict the value of that sample to be. And so we could artificially limit the number of nodes, the maximum number of nodes that a tree is allowed to have. And that would be another way of preventing overfitting from happening. And that's a hyperparameter in scikit-learn called max, I think it's max leaf nodes. So again, sort of same idea. Instead of controlling the depth of the tree, you're controlling the maximum number of different buckets that you're allowed to drop a sample into at the end of the day. Philosophically, really it's getting to the same thing. So anyway, a whole bunch of different parameters that get to the same thing with respect to decision trees, and they're all desperately trying to do the same thing. They're trying to prevent this tree from overfitting, which is a real hint that overfitting is a big problem when it comes to decision trees. Quick little note on overfitting as well. Actually, sorry, before I get into that, maybe I'll park the thought. Does anybody have any questions based on this stuff so far? Cool. Okay. Hopefully this all makes sense. Feel free to drop a comment too if you are curious about something. So, right. So one challenge with overfitting, and a common mistake that people make, is so you start off, canonically you separate your data into 2 data sets. You've got your training set, which is what you use to train your model, and then you've got a validation set, which is what you use to check to see if your model has actually just memorized the training set, or if it's actually learned things that generalize to unseen data. And that validation set is just unseen data. It's not data that you're training the model on. It's like a test, just like in school, you train on the textbook and then you go into class, you write a test. The tests are usually questions you've never seen before. The idea is to see, therefore, how well does your textbook knowledge generalize? Have you just memorized the words on the page in the textbook? Or are you actually learning principles that undergird a kind of broader, more robust theory of this problem? So that's the idea behind the validation set. Here's the thing. The validation set is the thing that matters in this context. It's like the main thing that you care about. If your model does really well on the validation set, then you have done a good job, or at least up to this point, you have done a good job. That's a really important thing to note, because a lot of people make the mistake of trying to optimize for the training set and the validation set at the same time. Let me kind of explain how people tend to approach this. We're taught to believe that if your model performance on the training set is really good, like 100% good, and let's say it's not as excellent on the validation set, that means that you're overfitting. Right? It means that you're performing way better on the data that you trained on than on data you've never seen before, which implies that some of the knowledge that you developed doesn't actually generalize the way that you hope that it would. Now here's where the problem comes in. People will look at that discrepancy. They'll say, well, I'm doing great on the training set, I'm doing perfectly maybe on the training set, and I'm not doing perfectly on the validation set. That must be a problem. Overfitting is bad. Oh, woe is me. I gotta make a really big change here and fix things up. But that's not quite right, because the only thing that matters is the performance on the validation set. And so you might be able to make the training and validation accuracies or performances approach each other. And then you could sleep soundly at night saying, okay, I'm not overfitting. My performance on the training set is almost the same as my performance on the validation set. But that's not actually the goal. The goal isn't to make those two performances the same. The goal is to make the validation set as good as possible. And it's very possible that the best performance you can get on the validation set will actually involve overfitting. Will involve getting 100% accuracy or 100% performance, however you're measuring it, on the training set. So don't be fooled into thinking that just because you're getting perfect performance on the training set, that necessarily means that you need to re-examine your problem and solve a bunch of issues. It's entirely possible that, yes, you're overfitting, but you still have the best performance you can get out of your model on the validation set. And that's the main thing you care about. So whenever you're approaching these kinds of problems, do try to think of it that way, like, what's the thing I really care about? And don't get distracted, thinking about overfitting as being this intrinsically bad thing. Overfitting can be a sign of a problem if your performance on the validation set isn't good. But if it's good enough for your purposes, hey, declare victory and move on. It can actually be not that bad a thing. So I'm just going to park that thought because it'll come back later. Does anybody have any questions about that aspect of this discussion? Cool. And I just noticed Charlene's just joined us, and so you'll know actually a thing or two about this as well because you're working on, I think, deep learning mostly, right?
Yeah, that's right.
Cool. So maybe I'll take this opportunity to flag that neural nets actually have this property like on overdrive, right? So overfitting, usually you want to start by overfitting your neural net and then kind of like reduce the amount by which you're overfitting. Is that fair to say, Charlene?
Yeah, especially if you're doing like a custom model where you've kind of rolled your own. It's pretty important to like make sure that your model even learns
Right.
before you try to train it on the whole data set. So that is a common technique that people use.
Actually, that's a great point too. Just like as a sanity check, making sure that your model learns. This is something that I like to do before, like if I approach a problem with just a simple decision tree or something, it's nice to let it grow as deep as it wants to go and confirm that, yes, I actually can overfit to my data. I actually can get that 100% training accuracy with this tree-based model to make sure that nothing crazy is going on in the back end. So anyway, a lot of reasons not to, let's say, make overfitting the boogeyman here. It's not intrinsically a bad thing. It's just a diagnostic. It's a thing to be aware that your model is doing. Cool. So that's decision trees. A little bit of an overview about the overfitting factor there. Now, one way that you can help to resolve the overfitting issue with decision trees is that while one decision tree might well overfit to your data, if you created a whole bunch of different decision trees and you average together their results, you will in general tend to get a better result than what you would have gotten with a single tree. This is something actually, it's a very well-known result in machine learning, and there's all kinds of interesting theory about why this happens, what this is called ensembling. So in French, an ensemble is a grouping together of different things. So an ensemble is just a group of models that you're putting together, and you aggregate their predictions in a certain way. The most common is just by averaging their output if you're doing a regression analysis, or if you're doing classification, just give each one a vote. See, if 80% of the models think that the sample that you're looking at is class number 1, then you guess that it's class number 1, and that's the prediction of the ensemble. So these tree-based models are an attempt to do that with decision trees. There's special kinds of ensembles that only use decision trees and no other kinds of models. So in general, an ensemble could contain a mix of logistic regression and a support vector machine and a bunch of decision trees. There's no reason you can't do that. But when people talk about tree-based models, they are referring to ensembles that consist exclusively of decision trees. And that can be a desirable characteristic because then you know that all of your individual models in the ensemble have similar properties and you can reason a little bit more consistently about them. So the first kind of ensemble that we're going to look at is known as a random forest. And this is like my go-to default model that I'll apply to certainly any kind of tabular data problem. It's a very robust approach, and it requires minimal hyperparameter tuning. So you don't have to get in too deep, that is, in terms of hyper-optimizing those hyperparameters. Usually, the out-of-the-box scikit-learn implementation is actually good enough to know whether your problem is easy or hard. When you're using a random forest, there are exceptions, but it's pretty robust. So how does a random forest model work? And that mystery, by the way, is going to get a little bit deeper. If you remember the decision tree session that we did 2 weeks ago, one of the things that you might have noticed is that decision trees are deterministic. So what I mean by deterministic is if you take the very same data set, the very same training set, and you train a decision tree on that training set, you will always and invariably get the exact same decision tree every single time. So there's no randomness in the process of training a decision tree. Take the same data set, train, model.fit on that data set, you will get a model that is identical to what you would have gotten if you ran that same code like the next time or 2 years down the road. The decision trees are perfectly predictable. If you have a certain training set, you are guaranteed to get a certain decision tree out of them. Another way to put that, if you want to get more philosophical, by the way, is a decision tree, in a way, is a property of a data set. You can view it as a property of a data set, just like an average. It's not actually its own thing necessarily, or at least most of the time. It's like once you have a data set, your decision tree is locked in. That's what it is. So, given that a single training set implies a single decision tree, we now have a bit of a mystery on our hands in terms of explaining how it is that we're ever going to have an ensemble of decision trees in the first place. If I can only ever get one decision tree from one data set, how could I ever get a number of decision trees whose results I can add together? I mean, doesn't a single training set mean that I would end up with like a whole bunch of identical decision trees if I tried to make an ensemble based on it? And so that's the first mystery with random forests, is somehow we're going to have to find a way to make these decision trees different. And there are two different ways in which this is done, or two main ways in which this is done. And they both involve basically changing the way the data set looks to each of these trees. So it is true that a certain data set implies a certain decision tree. There's no way around that. But if you change that data set, for example, by making some of its columns disappear, then you'll end up with a different decision tree. If you change that data set by making certain rows disappear or become invisible to a decision tree during training, then you will get a different decision tree. And those two strategies, making columns disappear or making rows disappear, are both used in random forests. So the way a random forest works is the random comes from the fact that you're taking a data set, training set, and you're removing a randomly chosen fraction of its columns and a randomly chosen fraction of its rows, and now you end up with a new data set. You'll train a tree on that, and there's your tree number one. That might be this guy over here. Next, you take the original training set, you randomly choose a different set of columns and a different set of rows, and that becomes, and then you train a tree on that new data set, and that becomes decision tree number two. And you repeat this as many times as you like. And we'll get into the point where you might want to stop, but that's the basic idea here. So you have a set of features. I think it's n_features in scikit-learn. And then you've got a set of rows, a fraction of the rows that you're going to retain as well. And so those are two hyperparameters that now your random forest can tune. So a random forest has all the same hyperparameters that a decision tree has. It has max depth, it has a maximum number of leaf nodes, it has all those things. And it also has these metaparameters that decide what fraction of the data set each tree is going to see, what fraction of the columns in the data set each tree is going to see, and what's the total number of trees in the ensemble in the random forest that you're going to have. And when you bundle those all together, I mean, that's already, I think that's going to be like 80% of the hyperparameters. You'll already know what they do when you look at the scikit-learn documentation. That's basically all there is to it. Actually, maybe I'll pause there. Are there any questions about that so far? Okay, just for kicks, I'm going to pick on some random people just to be a shit disturber here. Yannick, is everything cool? If you can't unmute yourself, no worries. Chris, is everything okay?
Yep. Yeah, sounds good.
Cool. All right. I'll take you to represent the ensemble here. So, all right. So we have these three hyperparameters now that are determined with our random forest. And, well, I mean, I guess I think that's pretty well all I wanted to say here. So samples basically you put a given sample into one of these decision trees. So you have a new sample that you're interested in classifying. You plop it into one of these decision trees, and it works its way down in the usual way to one of these final buckets where it gets classified or regressed upon. And then that same sample gets dropped into the next tree, and it gets sorted into a different bucket, and you get a different prediction from that tree, and so on, and you aggregate the results in essentially the usual way. So what's really interesting about random forests is just how robust this process is. The robustness comes from the fact that you're basically just like randomly choosing a new decision tree every time, and as long as you have enough different trees, like you're going to get a pretty consistent set of predictions that average out all the errors that any individual tree makes. And this is a good moment to talk about what those errors might look like and where they come from. So my favorite analogy to use when it comes to random forests is a democracy. I mean, it's no surprise, really, a random forest is a democracy of decision trees. But the analogy goes a little bit deeper than might initially seem. So first off, every individual in a democracy needs to be, to some degree, uncorrelated. If we were all perfectly correlated, if everybody was a perfect copy of me, then we wouldn't need democracy, right? We would keep electing whoever the hell I think should be in power, which is probably a terrible idea. So there's got to be a way that we decorrelate the individuals in a democracy. In other words, we need uniqueness. We need individuals who think for themselves. One way to do that is to have people who specialize in different occupations. So it's actually kind of nice that we have people who work full-time as economists, other people who work full-time at McDonald's, other people who work full-time as car mechanics, so that they can focus on the kinds of things that make the world better for people who work at McDonald's or in body shops and other places like that. And they're optimizing for those things. Those are the features that they're looking at in the world. They care about features that are associated with economics or working at a McDonald's and so on. And so really, we all walk around having done this feature selection. We've essentially kind of randomly selected a set of features, and that's what we see. That's the data set of the world that we see, and that informs our own electoral choices. In just the same way, if you pick two doctors, even though the feature set that they're looking at is actually quite similar, they're in the same occupation, the experiences that they have day to day are going to be different. So it's almost like having different samples now. Instead of changing the columns, they're looking at different rows. So the key is you want to have people with enough different experiences and with enough different lenses on the world that they're uncorrelated and you get to benefit from this wisdom of the masses. Now, here's a problem. If you look at a democracy and you just doubled the number of people, you created a copy of every person in that democracy, you wouldn't actually change the electoral output, you would just double the number of votes. So there is a point where you reach diminishing returns. If there's already like enough people that every point of view is represented, you don't really gain by growing the size of the population. And the same is true for random forests. So as you can imagine, especially if your number of features is small enough, let's say you have a very simple data set, just 4 different features, and you're trying to predict a fifth. In that case, you don't need that many trees in your forest before you're going to start running into trees that like have no choice but to be looking at the same set of features because like you've kind of run out of different features for them to look at. So in simple problems, you don't need as many trees in your ensemble. Your forest can be more sparse. And it's not always obvious what a simple problem is, which is why you want to actually tune that parameter. So you want to actually check your model's performance as you increase the number of trees. Now, the number of trees in the ensemble should actually be the last thing that you tune, just because, I mean, ideally you'd crank it up to 1 million and like you'd have as many trees as you need, and who cares if there's redundancy, I'll get a really good result, but that training takes time. So you want to optimize, you want to do all your hyperparameter tuning on all the hyperparameters that aren't the number of trees in the ensemble, get that right, and then as a final step, plot your model performance as a function of the number of trees. And what you'll usually find is a plateau point where, okay, beyond whatever it is, 5,000 trees, 500 trees, 50 trees, if your problem's simple enough, we really don't see an improvement by adding subsequent trees, so we might as well not spend half an hour waiting for models to train and cut things off at the lower number of decision trees and then go from there. So that's just one consideration that I think a lot of people don't necessarily think about when they're training a random forest or a tree-based model more generally. It's always worth looking at that. It's called n estimators and underscore estimators, the number of estimators, the number of decision trees in that ensemble in the scikit-learn docs. So always tune that one last and make yourself a nice little plot that shows you the performance as a function of number of trees. Anyway, nice thing to check up on. I'm just going to pause there. Are there any questions about that? Quiet bunch today. All right, Maya, I'll just pick on you. Is everything cool?
Me? Yes.
Sweet. All right, thanks. Okay, cool. So that's random forests in a nutshell. I guess I'm just trying to think if there are other things I could point to in terms of failure modes. Maybe I'll leave it there. The other kind of model that's really interesting is a slightly less naive one. So random forests are really naive. I mean, in a way, it's like it's the most brute force way of aggregating together trees that you could possibly imagine. You're basically taking like a whole bucket of decision trees and you're just kind of like shuffling it, randomly picking out a new one, adding it to your ensemble, and you do that for as many estimators, as many trees as you want in your ensemble, and there's your forest. And like, while that's really robust and that's great, it's also kind of boneheaded. I mean, in a way, you're entitled to ask, like, wait, shouldn't there be a thought process? Like between the moment where I reach my hand into the bucket and pull something out, shouldn't I kind of go, I wonder what the best next tree is that I should add to my ensemble before you just reach in? And the answer is you actually can do that. And that strategy is called boosting, or at least one way of accomplishing that is called boosting. So we'll look at another tree-based ensemble model, which instead of, or unlike random forests, isn't going to involve just like closing our eyes and reaching into some bucket of trees and pulling the next one out blindly. It's going to involve a deliberative process, a step in this process where we stop and we go, okay, I've got my first decision tree here. I'm going to step back and ask myself, given the problem I'm looking at, what is the best next decision tree that I could possibly add to this ensemble? And that is going to be called boosting. There are a whole bunch of different boosted trees that we could look at. I'm just going to look at a specific subtype called gradient boosted trees, which are here. That's how you spell it. And I'm just going to look at one particular way of making gradient boosted trees, but there's a whole family of boosted tree models. And these include things like, well, GBMs, or gradient boosted machines. They include things like AdaBoost. They include things like XGBoost. These all function using something that's philosophically very close to this. AdaBoost might be the most kind of qualitatively different one, but it's pretty easy and simple to understand. I can kind of gloss over it at the end of this as well. But yeah, so we're going to look at this gradient boosted trees concept. And to do that, I'm going to present you with an imaginary data set, much like the one that we were working with before. So we have the height, the weight, I wrote mass, I don't know why I did that. So height, mass, arm span, and some measure of athleticism that we're interested in predicting in the context. I really should have written like score or number of goals scored, something like that. That would have made a lot more sense in retrospect. Let's say that's what we're doing. So we're trying to predict the number of goals scored based on hockey players' heights, masses, and arm spans. Okay, so that's our data set. We are, actually, I'll add a little bit of color to our earlier conversation because I think there's one tie-in that's really cool here. We're gonna start by making a dead simple prediction using this data set. And I want to talk about why that prediction is still technically machine learning. So flipping back to our decision tree for a minute, I'll just zoom in a bit so you can see it loud and clear. You might remember that every bucket in this tree makes a prediction about the samples within it. So in this case, we started off, samples tells you how many samples there are at this stage of the tree in your data set. So 512 hockey players here. The value tells you the average value of the thing you're trying to predict. So we have here 512 hockey players. On average, they're scoring 21.4 goals. Now, the interesting thing with an average is it's actually technically a machine learning model. And most people don't think about it that way, but it really is. An average, what is it? It's a number that you can use to make predictions, and it gets better the more data you get. So really, that's no different from a logistic regression or a neural net. It's just, I mean, it's a very crappy model. It's massively underfit, but it is nonetheless a machine learning model. Data goes in, predictions go out, machine learning. So you can actually, the very first node in a decision tree is just an average. That's all it is. You have your data set. The samples in that data set have a certain average value of the target variable, the thing you're trying to predict. And like, you could actually call that a day. You could say, I don't even need a one-layer decision tree. I could have a zero-layer decision tree, and it would still give me a prediction. The prediction would just be the average. That's exactly what the first step of gradient boosted trees is going to be. We're going to create the very first node in a decision tree, which is just going to return the average value of the thing we're trying to predict. So it's going to take all of our samples in this entire data set, and it's just going to look at this athleticism column, just going to look at the number of goals scored, let's say, per season, the thing we want to predict, and it's going to average them up and give us a certain number. And that's actually represented by this bucket, this first kind of this first bucket in the blue here. That's what I'm getting at here. Okay. Any questions about that so far? Just want to make sure that's clear before I derail anyone.
I just have maybe not like completely related to this, but just a bit previously about how like in general an ensemble decision would work. So just to clarify, like if you had a group of different trees and they all might have like they're looking at different like features and things, in order to like aggregate their decision, say you had like a new data point coming in, you would just basically run that data point through like each of the trees individually, and then like either average their like predictors at the end?
Correct.
Okay. Thanks.
Yep.
I just want to make sure I had that clear.
You do. And actually, so that's just to kind of, I guess, extra build the intuition on there. It is also true that if assuming you only had one core on your computer and you couldn't parallelize this at all, if you had an ensemble of like 100 trees, it would take you 100 times longer to make a prediction than if you were using a single decision tree. So I don't know if that helps with the intuition, but yeah.
Yeah, no, that makes sense. Okay, thanks.
No problem. And Isaiah, I noticed you unmuted yourself as well. Do you have a question?
I was going to ask about aggregation as well.
Oh, so same question as Chris.
Yeah.
Gotcha. Cool. Yeah, and there are a whole bunch of, like I've talked here about the most common and maybe the simplest way of doing model aggregation, or more properly, like inference or result aggregation, I should say. You can take the average. You could take the mode, right? Like depending on the kind of problem you're facing, you might choose to ensemble in different ways. But the average or the like most common value for classification, that is, are usually the way that people do this. So modulo some fancy stuff that might arise, those are the ones you'll really want to think about. And anyway, not conceptually very loaded. Cool. So here we go. We define this very first node of our decision tree as like just the average. I mean, that's what it is. And we can just choose to represent that average as, the first node in a decision tree. And there we go. Now, if you were to do that, of course, while you would pat yourself on the back for having made a machine learning algorithm, because that sounds like something fancy to do, it's not a good machine learning algorithm, and so it will make a lot of errors. So if you just were to take this data set of hockey players and you calculate the average number of goals they scored, if you used that average as a predictor, if you were like, okay, they all scored on average, let's say 12 goals, so now I'm going to go ahead and assume that that's the number of goals that each individual player will score in the season, you would of course make a whole bunch of mistakes. And those mistakes have a special name when you're in the context, at least, of gradient-boosted trees. They are called residuals. Residual because they are what's left over after you've tried to make that prediction. So on average, these players are scoring 12 goals. Let's say we look at player 1 specifically, and we say, how many goals are they going to score? So you do average minus number of goals scored by player 1, and what's left over, that residual, is the error. And so that's what we're going to put. We're going to add like functionally a new column to our data set called the residual, which is just how much, how crappy basically was this estimate, was this average as a measure of the true value for every one of these different players. So every player will have a different residual because every player will, the number of goals that they'll score will differ from the average by a different amount. And so, right, so okay, I'm helpfully just writing out the same stuff that I already said. Cool. So what do we do next? Well, we're actually going to make another tree. And this time, instead of predicting athleticism directly, we're actually going to predict the residuals. So why might we want to do this? Well, what we're actually doing fundamentally, it's not unlike some aspects of what humans do when we try to learn. We try to focus on the mistakes that we made. And predicting the kinds of mistakes that you can make is actually a really great way of learning. So this is exactly what's going to happen here. We're going to say, okay, we have this average, which kind of tells us it's a really shitty estimate of like what all these players are up to. But now let's make another model to figure out what this residual is going to be. So we're literally going to feed this as the labels, the target variable for our next round. And we're going to feed in height, mass, and arm span as the features, try to predict that residual, and get a new tree. Now, what we could do at this point is say, okay, this tree, I mean, it's not even a stump. I mean, this node, I should say, is the average. The residual is being predicted by a more sophisticated tree here. And in theory, this tree is kind of like making up for the errors that were made by the first one. Right? That's kind of the way to think about it. The first tree just gives you a naive average. The second one goes, you know, I've learned from my data set that, like, for this particular sample, I tend to make this kind of mistake. So for, let's say, for particularly short players who are particularly heavy with short arm spans, then I tend to, overestimate the number of goals that they'll score using the average. So I'm going to reduce that. My prediction is going to be that the error is going to be very strongly negative. And so what you'll do is now you put a new sample in the first predictor here. You get an average value. You put another sample in here, and then you add together those predictions, and you get something that is a lot closer to the truth, right? Essentially, the second tree makes up for the errors of the first. Does that make sense? Does anybody have any questions about that piece?
So you make sure you like exclude the feature that you originally used to calculate the residuals, right?
Yeah, that's right. So you're right. So the athleticism or number of goals scored, which was what we were trying to predict here, we ripped that out. Yeah, ignore that column and almost like replace it by the residual. Yeah.
Okay. And then do you always use like all of the other features, or is there some way to like, do you ever use just like a subset of them or look at combinations?
So you actually could, right? And that would be like a kind of cool hybrid random forest and gradient boosted machine type thing. And I'm sure somebody's written a paper on that. But typically with gradient boosted trees, what you're doing is just looking at all the features. The thing that's different about those trees is now that they're predicting a different thing.
Right. Okay, thanks.
Yeah, no worries. But your instinct is bang on, by the way. Like it's almost like any mechanism that causes your trees to be different is fine. It's just that some are a little bit more useful. And in this particular case, this process of training on the errors that the previous model makes just tends to make a little bit more sense, and your model will be better off for being able to see all of the features as it does that.
Right. Cool.
All right. So great. So I'm going to pose a question, though, at this point, which is, suppose that this tree right here actually does like a really good job, right? If this tree is really, really good at predicting the residuals, then we're just kind of going to get a perfect answer on the training set. In other words, we're going to overfit again. Like if this second tree can grow as deep as it wants, we're going to have problems. Like we're going to be right back to square one with a model that just overfits like crazy. And we would like to not have that happen. So I hope that statement makes sense, by the way, because it's a pretty heavy statement. So what I'm saying is we take the average here, okay, fine. Then we figure out the residuals, the errors that we make when using that average to make our predictions. But now if we train a single decision tree that goes super, super deep, or however deep it wants to go, or even just decision trees tend to overfit, we'll likely end up with like perfect predictions on the training set coming out of this tree. So when you add these two together, you're going to get the average plus the exact right residual, and you'll get no error. So in other words, overall, this thing is going to be overfitting as well. I hope that makes sense, but please stop me if that's confusing. Okay, I'm going to assume that that's good. So then where does this leave us? I mean, like, have we basically just like gone around in a giant elaborate circle and now we're right back to where we started? Well, the answer is no. The answer is there's a way out of this, and that way is by not adding a whole tree like this, but instead a little bit of that tree. So we're going to take our initial prediction, right, our average, and then we're going to add to that prediction a small number, let's say 1/10, 0.1, times the prediction of this potentially overfit tree that was trained on the residual from the first tree. And basically what that's doing is it's us taking a little step in the direction of correcting for the errors from the first tree, but not going all the way, not risking overfitting. And now we're going to get a new residual that has a slightly lower error because it's been corrected for by the second tree. So in other words, if you take a new sample, a new player, you put them in this tree, you get a prediction. You put them in this tree, you get a different prediction. You add the prediction of this tree plus 0.1 times the prediction of this tree, and now you're going to get something that's a little closer to the truth, but not perfect because you've only taken a small step in the direction of correcting for the error of the first tree. So the next step is going to be to repeat this process. We create a new residual column. And this column has the errors that we're left with after the first tree plus this little step times the second tree. That new residual lets us train a third tree, and we just repeat this process iteratively. Every time we take a little step in the direction of fixing the errors that the previous ensemble of trees created. So this is us really reaching into that bucket of decision trees and going, what's the best next tree that I could pick based on the errors that previous trees have made, that the entire ensemble previously has made. So it's a very thoughtful process. It takes longer to train using this method because it's not completely random, but it does tend to work quite well, and that's the gradient boosting and gradient boosted trees. This number here, the 0.1, is called the learning rate. So when you're training a gradient boosted tree, you actually have to specify one of the hyperparameters is going to be that learning rate, and then you're also going to have the number of trees hyperparameter and all the regular decision tree hyperparameters that you've seen before. So the learning rate is going to be one of the new ones that you might not have seen before. Any questions about that? I think that there's a fair bit there. So, Adam, you cool?
I just have a quick question. So that, oh, sorry.
Yeah, sorry,
go on.
Sorry, I think Adam's good. I think he muted himself. Or Adam, if you have a question, feel free to unmute. But
no, go ahead, Chris. Go ahead.
Okay, sorry.
Okay.
Go ahead.
Yeah, I was just wondering. That's really cool. I guess that's where the gradient idea comes from. Does the learning rate actually, like similar to an, like I guess gradient descent or something like, or at least your step rate will change like the closer you get to like your local minima or whatever. Does the learning rate here, like, is there versions of the model where it changes as you kind of approach like a smaller and smaller residual or something like that?
Yeah, absolutely. So this depends on the implementation. I'm pretty sure in the scikit-learn version that you just specify a fixed learning rate, though you can have custom, I'm pretty sure you can have a custom learning rate function. I'm pretty sure this can be done. But yeah, in general, you're right. So I'm just going to pause on that for just a second. So Chris's point, the analogy with neural networks and gradient descent there is, so neural networks do the same thing basically. They start from some values for all their parameters, and you figure out basically like what's the direction we need to move all these parameters in to improve the result that we're getting. And then you move all those parameters in that direction by a step that's actually called the learning rate. It has the same value. So it's maybe 0.1 times the gradient that each of these, in this case, that each of these parameters experiences. Now, the problem with this is as your model gets better and better over time, it's kind of like with human beings, like early on when you're learning something, you're making very big updates to your model of the world. Like you're going, like when you first learned about the Big Bang, you're like, oh my God, this like came out of nowhere and how crazy. And over time, as you refine your understanding, the tweaks to your model of the world become more and more refined. They become smaller and smaller. Rather than taking radical life-altering steps every day, you're instead like kind of, realizing, look at that, I missed a minus sign. There's cosmic inflation. Maybe it didn't start from like a singularity. Maybe it started from something very, 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 very small, but not quite a singular. And these are smaller and smaller adjustments that we have to make. And it's a converging process. You need to lower that learning rate because if you keep making really big jumps, if you keep going like, oh man, my model of the world needs to be tweaked in this direction, but you don't reduce the amount by which you jump, you're never actually going to zero in on the true answer. You're never going to, it's like circling the drain almost. You're never actually going to find the friggin', the drain. You're never going to find the drain. You're going to keep kind of bouncing around the drain or bouncing around the optimum unless you start to reduce the step size, and it'll become a converging process. So, Chris, to your excellent question, the learning rate here is generally fixed. I want to say for conceptual simplicity, I'm not too sure on that, but if actually somebody else might have a better sense. Does anybody happen to know this? In scikit-learn, I mean. Yeah, Mai?
I'm not so sure about this as well, but my perception is that you tune it and then you decide based on how you tune the parameter. And I actually have a question on that as well.
Okay, great. Actually, I will just toss in one clarification there. You're right, you do tune the learning rate. It's another hyperparameter that you can tune. But I believe Chris's question was about, like, how do these values, like, is the learning rate the same at every step? Like, so for every new tree, are you always doing 0.1 times that new tree? In other words, are you always taking a step of the same size?
Hi, Jeremy. This is Kiran.
Yeah,
So,
Kiran.
after my experience in scikit-learn, you go with just one number, like in every step.
Okay. Yeah,
Yeah.
great. Thanks. That was the answer we were looking for there. Cool. Yeah, and I think that's been my. Oh, go ahead, Chris.
Yeah, no, thanks. I guess that like, from a practical sense, yeah, like there's probably, like you said, like a diminishing return if you're continuously adding more and more trees with smaller and smaller steps. Like they're really having like maybe a negligible impact on your kind of final accuracy. So probably at some point you would just say like cut it off and say, okay, we get good enough performance that we need without adding a bunch of extra computation time or whatever.
Yeah, absolutely. Paris.
Can I ask you a question too?
Yeah, of course, go for it.
Well, like at the beginning, when you were saying for like selecting these trees, we have to like it selects like randomly some rows and columns because in a sense of rows, it doesn't make sense to me because like this way you are displace the data, like like it just doesn't make sense to me. If you can like give more explanation on that.
Yeah, definitely. This is a really good question, by the way. So I'll just flip back to our random forest illustration here. So the idea is, if I take a certain data set, and let's say that we're going to keep all the features the same, so all the columns are still there. If I want to get a different decision tree out of that data set, somehow that data set's going to have to change. And the only approach that I can think of to change that data set is to remove at that point rows. If I'm not going to remove columns, I have to remove rows. And so effectively, that's what's going to end up happening is we hide, usually it's somewhere around 30% or so of the rows from the decision tree while it trains. And then we'll get tree number 1. And then we hide a different randomly chosen 30% of those rows from decision tree number 2 when it trains on the same data set. But now that data set looks different because it's missing a different 30%, and so on. And so we actually, it's just a way of basically decorrelating those decision trees so that they learn to approach the problem using what I'll call a different thought process. So it's almost, oh, sorry, yeah, did somebody have a question there?
No, sorry, that was my phone. Sorry.
Oh, sorry, no, yeah, no worries. So the idea here is to build an intuition for this. You can imagine, so let's take the column example to start because it's the most intuitive. If I were to tell you, okay, build a decision tree to solve this problem, here's the data set, the full data set, right? So you use all the columns and all the rows and you build the decision tree in the usual way. But now if I tell you, I'm going to hide 30% of the features, and I want to see you try to solve the same problem, chances are you're going to have to use a different strategy. The kinds of things you'll look at, the kinds of thought processes that you'll engage in as you try to work your way through solving this problem are going to be different. You're going to have to pay more attention to certain features because now you can't use the others as a crutch. The same is true with actual samples, with rows in the data set. Sometimes there are data points that give a disproportionate amount of the information about where the decision surface should be. And so those data points are like way more valuable. So if you don't let a decision tree see those points, it has to learn to use other points. And maybe it'll develop a different thought process. And that's really the mechanism by which it becomes decorrelated, by which it starts to develop its own thought process. It thinks for itself in some sense. And that's really what we want. Does that make sense?
Yeah. And so it's kind of like shuffling all the data points somehow too for this correlate them, right?
Exactly. That's the goal.
Okay. Got you. Thanks.
No problem. Yeah, so that decorrelation is really fundamentally important in any system that relies on ensembling, because as we discussed, right, you can easily double the number of estimators, of machine learning models, without actually improving the quality of the prediction, because what you're relying on is, hopefully tree number 1 is gonna learn to spot problems that tree number 2 can't spot. And the hope is that by having this kind of interesting jumble, this mix of different trees, that you can actually cover all the blind spots and end up with an all-seeing model, or at least that's the philosophy, that's the dream. There's another thing I want to toss out when it comes to random forests. Damn it, now I can't remember. Are there any other questions about any of this stuff? Yeah, Mai.
Yeah, so I was just curious what your thoughts are on so tuning learning rate and performance speed. I think I run into some problems with learning rate of random forest at some point, tuning for a really large data set, and it became really slow, even if it improves my performance. So what's your thought on that? How important is the trade-off there?
And so I'm wondering is it possible that by learning rate you meant number of trees in the ensemble?
Yeah, and the depth,
okay,
and all of these features that we're tuning, right?
Okay, gotcha. Yeah, so learning rate intrinsically is, you can think of it as like in a way the boldness of the model, like how much of an adjustment are you going to make in your model of the world when you find out that you're wrong, right? So like an example of this would be, if you were trying to predict the U.S. presidential election, and you had a certain model of the world that said like, yeah, I am confident that candidate number 1 is going to win. Like I'm so sure, and then you're 100% positive, maybe you even bet money on it, and then it turns out your candidate doesn't win. Like, should you make a really big update based on that one data point? Should you say, oh my God, my whole model of the world needs to be radically changed? If you do that, then you're applying a very high learning rate. And that doesn't mean you're learning a lot. Like, those are two distinct things. You're just making a big adjustment. That actually could be a bad thing. You could overcorrect. That's, people say, I think you're overcompensating. They're saying, I think your learning rate is too high. And conversely, you could do the opposite, right? You could say, well, not a big deal. I'm sure my model of the world doesn't need to be updated, and most of us usually do that because it's a lot more convenient and it feels less straining. So the learning rate itself doesn't cause the model to consume more time in training. It's more like it's going to affect whether your model actually converges on a kind of global optimum or a really good value. So it's more like a hyperparameter that you just have to iterate through. Where I suspect you were going in terms of the training time issue, the one variable that will absolutely increase the performance of your model as you increase it is the number of estimators, at least as long as your estimators are uncorrelated. So as you add more decision trees, yes, your model's performance should go up. And yes, you're right. It will, especially on big data sets, take more and more time. Because as we discussed, I'm trying to remember, I think it was Chris who pointed this out. He's like, or something I said to Chris at one point anyway, if you multiply by 100 the number of trees that you're using to make your predictions, it's going to take you 100 times longer to make your predictions or to train your model, right? So more trees is more compute time. And there's a trade-off. At a certain point, you need to step back and walk away. If your data set's really big, well, you're not really going to have like 1 million decision trees unless you're working with a supercomputer or unless you're OpenAI. Most people operate with more stringent constraints, and that's okay. So then the only question becomes, all right, well, when do I declare victory? When do I say enough's enough? And this is a different office hour, I talk a lot about the importance of setting a win condition before you even start your project. And I highly recommend doing that for exactly this reason. So if you know that your model has to be 85% accurate or have an F1 score of 0.9 or whatever it is ahead of time, that's your walkaway condition. If you reach that threshold, declare victory and move on. So what you would do in that case is, you plot out like number of estimators, number of decision trees as a function of the thing you care about. Let's say it's accuracy, and you hit 85%, and you're like, all right, how many trees is that? Great, and can I afford to wait that long? And if the answer is yes, perfect, you've got your number of trees. If it doesn't work out that way, if it turns out that you don't reach your target accuracy level for the amount of time that you're willing to put in, then you have a deeper question to ask about, number one, should I try a different model? Number two, should I go back to this probably should be number one. Should I go back to collect more data, do more feature engineering, try to come up with do some feature selection to narrow down the number of features I'm using, that sort of thing. But that's where you get into those fundamental questions. It's possible you won't even have to ask those. If you very often, you just add enough estimators, you'll hit your win condition, and that'll be that. Sorry, I think I rambled on there, but did that answer your question?
Yes, definitely, and thanks for the clarification.
Oh yeah, no problem at all. Cool. Any other questions? Maybe we have time for maybe one more here before we... Oh yeah, Kieran.
Hi, Jeremy. So what should be the good starting point in terms of learning rate? Should it be a default value, or should you try and see which one is giving you a better result, like just when you're starting your model?
Yeah, this is a really good question. And in general, it's rare that there are good answers to questions like, what's the best starting value for my hyperparameters? Usually this is a matter of trial and error to some degree. The default values in scikit-learn are usually pretty good, to be honest, like to start with. The learning rate is a pretty influential hyperparameter. It's actually worth tuning that one. But one thing I really would advise against or caution against is the risk of getting stuck in like hyperparameter optimization purgatory, where you just because the problem with optimizing hyperparameters is it's like your classic beat your head against a wall for no reason problem. There's a really well-defined metric that you can optimize. So you can tell yourself, yeah, I'm working at the right part of the problem here. There's this clear metric, and it's very easy to throw a bunch of muscle at the problem, throw a bunch of compute at it, and try every possible combination of every different hyperparameter. That's a seductive combination, and it's very risky in the context of machine learning because it's actually quite rare that hyperparameter optimization will be responsible for a big uptick in performance. Usually, it's worth trying a couple of different combinations. Oh, okay, sweet. Yeah, this is exactly the kind of exemplar I was hoping for. Is it Charlene? I don't know if you want to share that verbally, but
yeah, I was just gonna say, I recently got access to weights and biases to run hyperparameter optimization sweeps while I was training one of our models, and it turned out that it actually didn't make a very big difference in performance, even though it ran for hours and hours. So if you want to save the environment or just ship a model that's already pretty good and not spend too much more time on it, I think you can probably skip that.
Yeah, and that's coming from somebody who works on neural nets, right? So that's a very, your hyperparameter values can change a lot more to some degree. So yeah, pretty, thanks for that, actually. I think that's a really good perspective.
Yeah, and the one that is important is learning rate, like you mentioned. So learning rate did make most of the difference in the one case that I mentioned.
Right, and actually, it's interesting that comes up. I should have connected it, but you're totally right with neural networks. It's super important. It's also super important in with your what do you call it? Gradient boosted trees, right? So this is a common refrain. Optimizing other things yeah, you can get stuck in a rut very quickly. So I don't know, time box it, I would say. Definitely don't jump into it and say, I'm going to optimize my hyperparameters till I get to this level of performance. You probably won't, and it's not a really valuable skill set to develop. It's not a differentiated skill set to be really good at hyperparameter optimization. Grid search CV is your friend. Even if you want to use Bayesian optimization, there's a scikit-learn package for that. Random search CV is great, but cap it. You don't want to be putting in too much time. Oh, sweet. Yes. Geez, sorry, Hangouts making it really tough to click on that chat. Charlene says more and higher quality data is always, yeah, that's right. So more data, better data, yeah, perfect. Okay, this is great. Okay, everybody go listen to Charlene. Collect more data first, do your hyperparameter optimization second, and do it only if you're looking for that extra little boost at the end of the day. It's not going to be that decisive usually. So with that in mind, maybe I'll park it there. If you guys have more questions, feel free to share them on Slack or wherever, and I'll be posting the video of this later today.